Hi guys, in this video I will cover the Wittig reaction. It's spelled with a W, W-I-T-T-I-G. Looks like Wittig, but it's pronounced Wittig. German chemist by the name of George Wittig developed this reaction. He actually won Nobel Prize in 1979. And he actually shared the Nobel Prize that year with H.C. Brown, who was the developer of sodium borohydride. The Wittig reaction, as you might expect, being named after a chemist who developed it, is a very important reaction in organic chemistry. In terms of functional group transformation, it's essentially, we can consider it converting a carbonyl to an alkene. It's a great way to make alkenes, with a carbonyl compound being one of the starting materials. An example of a Wittig reaction, we have this ketone here. And we are reacting this with this reagent, which is a little bit odd at first. It's a phosphorus double bonded to a carbon. Phosphorus has 3 R groups, 3 phenyls in this case. And this is called a phosphorus ylide. We'll look at this closer here. The aldehyde or ketone reacts with the phosphorus ylide to give an alkene. Typically, only thing else you may see here is a solvent. Now, there will be some variations in this reaction we'll show below. Now, a byproduct here, the fate of the phosphorus is it becomes this phosphine oxide. Ultimately, this reaction, if we sort of focus in on what's going on here, you've got a carbon double bonded to an O and a carbon double bonded to a phosphorus. In the end, these 2 carbons are going to be double bonded to each other. And that's a great way to think about it initially. And the other group on this carbon, in this case a methyl, is still on that carbon. But that carbon is now double bonded to the carbon of the carbonyl. Now with alkenes, we may have potential for isomers if the alkene is stereogenic. This one is. So I'm showing a E isomer here. We're also going to get Z. The Wittig reaction is a great reaction. Lots of pluses to it that we'll mention. One drawback, if you may, is the product tends to be a mixture of E and Z isomers. Although in specialized cases you may get one preferred over the other, but that's going to be beyond the scope of what we'll be looking at. Okay. So the carbons become double bonded to each other, and the phosphorus actually becomes double bonded to the oxygen, as shown here. Now this is a resonance structure, that's a resonance structure. So it's almost like trading dance partners here. Okay, the phosphorus ylide. First off, an ylide, funny looking word, Y-L-I-D-E. An ylide is a name or is a term for a net neutral compound, but it has charges that are adjacent to each other. So it's 1,2 dicharged. To be net neutral, one's plus, one's minus. And we see that here. Now, this structure, which I showed up here, is just a resonance structure of the dicharge structure. take these electrons and move them in here, we get this resonance structure. Now, going the other way, now both of these resonance structures are important for considering here. This one, you kind of look at and say, okay, that carbon is double bonded to phosphorus. It's going to become double bonded to the carbon of the carbonyl. So that resonance structure is just good for kind of predicting your product there and sort of visualizing how things are put together. This resonance structure is going to be more important for our mechanism because it illustrates that this carbon has carbanion character. And that carbon is going to be the nucleophile in the first step of the mechanism. To get to this resonance structure, we just take these electrons and move them here, and that gives that resonance structure. Now, this is a little bit sort of, well, why didn't we move them the other way and make the phosphorus minus and the carbon plus? That's a very reasonable question. I'm not sure I can answer that. One thing we're doing here is this is an expanded octet on phosphorus. And it could very well be that phosphorus doesn't like to expand its octet beyond 8. So, we do understand that it's polarized in this direction, and this is an important resonance structure for mechanism. It's a net neutral compound, though. Okay, mechanism. If we have this carbanion, which this reagent, okay, if we know resonance, this reagent can exist like this, partially, the true structure somewhere in between. Mechanism is this carbanion, these electrons add to carbonyl, electrons up. That's going to give, let's make sure, here's the carbon that just bonded. It has a methyl and a phosphorus with 3 phenyls. The carbon with the methyl is now bonded to the carbonyl carbon. Electrons up. I'm actually going to draw it this way, but electrons move on to oxygen. Becomes minus, right? We just made this bond. Electrons on to oxygen. Bond. Electrons on to oxygen. The carbonyl carbon has a methyl and a phenyl. I drew this like this because I wanted the oxygen and phosphorus right next door to each other. Of course, the new bond we made has free rotation. It can swing away either way. But we know from physics that these opposite charges attract. And the next step is these electrons then add to the phosphorus. Phosphorus can take on more electrons. It can expand its octet just like we did in the resonance structure up here. But that's resonance. This is not resonance. Here we're making a sigma bond, and that leads to this structure here. And here, this intermediate in the mechanism, oxygen is neutral, but so is the phosphorus. Phosphorus has 1, 2, 3, 4, 5 bonds. There's no lone pair there. And we get this 4-membered ring. Now this 4-membered ring is not stable. It cannot be isolated typically. It continues on. This is going to undergo a rearrangement. And it rearranges to the final products up there. The rearrangement, we could start in different places. Let's start with the oxygen. Oxygen makes very strong bonds to phosphorus. In chemistry, lots of elements make strong bonds to each other. For example, fluorine and silicon makes very strong bonds. That's why fluorine or fluoride will etch glass, which is largely silicates. Oxygen and phosphorus also make strong bonds. This oxygen would love to make another bond to phosphorus. That's my sort of colloquial explanation. These electrons here. But phosphorus can't make any more bonds than it already has typically. And so when these electrons come in, these other electrons move away and they move over here to make double bond between carbon and carbon. Well, this carbon can't make 5 bonds, so something has to leave. Well, the oxygen essentially leaves and it gets its lone pair back. And this electron movement gives final products. I'll show them again if you like. We now have double bond between the 2 carbons. There's a methyl, and there's a phenyl. We also have the phosphorus with 3 phenyls. Can I just draw them like that? And it's double bonded to oxygen now. And oxygen should have 2 lone pairs. 1 remaining plus the new one that came when the bond broke. And that is the same as I have shown above. Now, the E and Z, again, I have shown E here. It's going to be plus Z. The E and Z comes from here. You have free rotation here. And you're going to get variable outcomes at this point. The 2 methyls, I didn't show stereochemistry, but the 2 methyls can be cis or trans at this point. And thus you can have them effectively cis or trans in the alkene product. Okay. So this is sort of a decomposition, sort of a retrocyclization. The ring is opening back up. This is again largely driven by oxygen wanting to double bond to phosphorus, and we get the alkene. So this reaction, like many reactions are, discovered. This was discovered by the chemist Vinegar, German chemist, and developed and studied, etc., and became a very widely used method of making alkenes throughout like the 1960s and on, and remains an important reaction today. Okay. So, how do we make these phosphorus ylides? Well, it's actually pretty straightforward. We start with an alkyl halide or some tetrahedral carbon with a leaving group. Most common alkyl halide, of course, you could have tosylate, etc. And triphenylphosphine, which is actually a very nice stable solid. And it's a good nucleophile, and the lone pair will come in here and we can get it to displace the bromine. A lot of times this is done with a little heat, some type of solvent. Refluxing for an hour or 2 or longer. And we get this, what's called a phosphonium salt. Which if you put this together in the solvent, maybe like chloroform or dichloromethane or something, a lot of times you heat this up and you get a precipitate. And it's the salt here, because the ionic compound here, the salt, is not as soluble as the 2 neutral starting materials. And so these tend to be relatively easy to isolate. Now the salt, because the phosphorus is positive here, these H's have some acidity. And if we include a base, we can deprotonate this, and we can generate the carbanion. And the carbanion is stabilized by, well, resonance. There's the carbanion here, and we showed resonance. But it's also stabilized because it's a net neutral compound. And you've got this sort of charge attraction. And the phosphorus kind of wants electron density, and so it's sort of pooling here. But it's a carbanion that we can make fairly easily because of that positive phosphorus. A variety of bases can be used here. You can use a very strong base like N-butyl lithium, very common, but you can also use weaker bases, even hydroxide bases, even a base such as phosphate, like sodium or potassium phosphate, which, if we do the Vinegar, the Vinegar that we typically do in my Organic 2 class uses potassium phosphate. Of course, if you used hydroxide would take an H, would make water, and then the potassium ion would sit with the bromide ion, and we would generate an equivalent of KBr. So it's possible because of the positive phosphorus. Why triphenylphosphine? Well, other than because this is very common and it's very stable, it's a solid, very easy to use. Why not trimethylphosphine? Well, the main reason is we don't want H's, a CH on the other side of the phosphorus. If we had a CH on the other side of the phosphorus, we would have two different sites that we could potentially deprotonate. Because there's phenols over here, the adjacent carbon does not have an H, and we're only going to deprotonate on this side of the phosphorus. And so essentially the phenols here give us the inertness that we want, so we only deprotonate at this site. Now, in practice, many Vinegar reactions don't actually use the ylide as the starting material. Very often you start with the phosphonium salt, and you add in your aldehyde or ketone, but you also include a base. And the first step in this reaction is formation of the ylide in situ. That is, we first do the base extraction of the proton, generate the ylide, then when the ylide is generated, it immediately reacts with the aldehyde or ketone, and the reaction, the Vinegar reaction, essentially then takes place to give your alkene. So this is essentially, the phosphonium salt is sort of an ylide precursor. And this is common, and in fact, if we do the Vinegar reaction in the course, we will do this way. We will include a base and generate the ylide in situ. Okay, on the next page, some homework for you to try. Show the product of this Vinegar reaction. Again, guys, in this case, it's pretty much, it's just prompted here. You see a phosphorus ylide double bonded to phosphorus, aldehyde or ketone. The carbon here is going to be double bonded to this carbon. It's just switching partners. Instead of carbon double bonded to O, it's now double bonded to this carbon, which is double bonded. And the phosphorus becomes double bonded to the O. So look through that. You need to be able to see that on your own. Then we also need to think about going backwards and using a Wittig reaction or Wittig synthesis to make various alkenes. Show a Wittig synthesis to make alkene A, and then show a Wittig synthesis that would give alkene B. Now, you actually have two choices here, because one carbon comes from the carbonyl, the other carbon comes from the ylide. They just changed dance partners. But which carbon do you want to be the ylide and which carbon do you want to be the carbonyl? Back over here. The lower carbon of this alkene was the carbonyl, and the upper carbon of the alkene was the ylide. Okay? And that's actually designed by purpose. The less substituted carbon of the alkene, that's the one that you want to be the ylide. So this was the ylide carbon. And this was the carbonyl carbon. The reason we want the ylide carbon to be less substituted comes from the fact that it's made originally starting with an SN2 reaction. And you want your SN2 to take place at a less substituted carbon. So you want the SN2 to originally take place at a primary carbon instead of a secondary carbon. So keep that in mind. So back over here, this is going to originally be a secondary carbon, or kinda. Certainly if we consider them originally tetrahedral, that'd be originally a tetrahedral. If so, and if this was the tetrahedral, it would be primary, and you'd rather have that be the ylide. Think about that though. Show the ylide, show the carbonyl compound, show the ylide, show the carbonyl compound. Also think about doing your reaction by the in situ. Okay, in situ approach, where the ylide is formed in situ, meaning in the reaction. Okay, great way to make alkenes. Now, let's think about this though. How did we make such an alkene before? Give us a chance to review our alkene chemistry a little bit. A synthesis of compound B that we should already know. If we start with this carbonyl compound, we could do a Grignard. Methyl anion in, electrons up. Pick up a proton with work up. Tertiary alcohol. And then dehydration of an alcohol is a common way to make alkenes. Acid catalyzed E1 dehydration. And that would give compound B. Problem is that would be a minor product. That would be the Hoffman product. The major product would be this alkene, the Zaitsev product, because this is a tri-substituted alkene and that's a di-substituted alkene. So actually B would be a minor product here. One of the great things about the Wittig is it is regioselective. All right, this is not regioselective. Now, the Wittig, as we said, is not typically stereoselective. Both stereoisomers of the alkene, when stereoisomers are possible. So it's not stereoselective, but it is regioselective. You don't have to worry about regioisomers. And that was one of the big things of the Vitig when it came along and when it was developed, because many other reactions that give alkenes, you get different regioisomers. Okay, so give those a try. We'll look at those later. On the next page here shows some drug synthesis, and it shows a Vitig reaction. It shows two of them, I believe. Here, they're making a phosphonium salt by reaction of this benzyl bromide with triphenylphosphine, toluene reflux. Phosphonium salt, that's 10. Then they come in with an aldehyde ketone and base. Okay, this is in situ formation of the ylide. And then the ylide reacts with the aldehyde, give the alkene. This is, I don't know that we've seen this before. This is an alkene, but they're showing this sort of squiggly bond. This is sort of a way to indicate that it's a mixture of E and Z. The phenyl is both up or down compared to the other phenyl. It's either trans or cis to the other phenyl. They're showing a 50-50 mix of the alkenes. Then they're doing other chemistry out here. Down here they're doing another synthesis of a phosphonium salt, this time benzyl chloride, DMF reflux. That's a pretty high temperature there, DMF reflux. Then they're doing the Vitig using potassium carbonate. It's got some different chemistry going on here. They've got this ring over here with one of the nitrogens being an oxide. I reckon they're not quite sure which one, or it's a mixture. And then somehow in the Vitig reaction, it looks like the oxide was reduced. Well, only a very minor bit. It looks like they only got 3%, but a minor impurity. Perhaps because of the phosphorus being there for some reason. Oxygen loves phosphorus, and somehow the oxygen became bonded to the phosphorus, but not sure of mechanism there. And there's some method development down here. You can take a look at what they're doing here. They're looking at different solvents. By the way, the 18 Crown 6 is a Crown ether. This is actually a variation of the Vitig where I think it's been shown that the Crown ethers help give one alkene isomer over the other. When the Crown ether is used, I think that's a Bowden modification, which they're calling this a Vitig Bowden. So it's sort of a modification of using that, trying to influence the outcome of the EZ ratio. Okay. Essentially, though, that's just showing you an example. If you want a full paper, the full reference is up here. And if we do the Vitig lab in this course, it's here in the workbook, and starting with a phosphonium salt, aldehydes in this case, of course it could be a ketone, using potassium phosphate. And the unique thing about this particular reaction method is we're going to be grinding the reagents without any solvent. So no solvent, grinding. And as this lab is written, there's a variety of different aldehydes that can be used depending on the R group. And different choices of R groups are here. And we may assign those R groups in class before we get to lab. That way you can find a literature melting point before you get to lab. So there is a VIDIG to do. Going green in the laboratory. In this case, a solventless reaction. Okay, guys, that's the VIDIG reaction. Take a look at the couple of homework there. Make sure you can put these together, and there should be questions for practice in the workbook and in your textbook.